So the key step in this question is to recognize that if I move the m squared term to the other side, this will be the familiar difference of squares identity. And I can write this as n minus m times n plus m, and 105 is an integer here. We're looking for positive integers. So essentially it's about how many different ways I can factor 105, and I can list all the factors, 1, 105, then you go to the next one, which would be 3, 35, and then 5, 21, and then 7, and not 7, yeah, 7 and 15. And you would also know that if you were to do the prime factorization, if you want to absolutely make sure that you haven't missed out any factors, you do the prime factorization, and which would be 3 to the 1, 5 to the 1 times 7 to the 1. So number of factors would be you add 1 to each of these exponents and multiply that. That gives you 8, and we do indeed have 8 here, and that includes 1 and the number itself. So if that's the case, and we can write 105 as 1 times 105, then we can say, since these are also integers, n minus m is 1, n plus m is 105, and we can solve for n and m. Here 2n would be 106, n is 53, and then m would be 52, and you'll see that this does indeed satisfy. So we have to do this for the other pairs of factors as well. We have 3 and 35, and because I absolutely want to make sure that I'm not making a mistake here, I'll do all of these quickly. 3 times 35. I'm always equating the n minus 1, which is a smaller number compared to n plus 1, with the smaller factor here. So n minus m is 3, n plus m is 35. Again, if I add this, n would turn out to be half of 38, and then m would be 16. So that's another pair. Second pair. So each one is giving us one pair. Because these are all odd, and these are also odd, we know that when we add them, it's even, because we'll get 2n, and so they will all work. So if we do 5 and 21, this is 5. n plus m is 21, so we'll get 2n is 26, n is 13, and m is 8. That's another pair. And then finally, this one will also work. N minus m is 7, n plus m is 15, and again, n would be 11, m is 4. So we have 4 such pairs, and they're right here. These are the 4 pairs that would give us distinct values for n and m. So the answer is 4.